Welcome everyone to RMIT Distinguished Lecture. I'm Xinhu Yu, the chair of RMIT Professorial Academy and the host of this event. First, I would like to acknowledge the people of the Kulin Nation on whose unceded lands we are meeting on today. I respectively acknowledge their elders, past and present. So today we shall hear from Distinguished Professor Andy Ball, a lecture on transforming Australia's biosolid industry. So this is a part of the activities hosted by the Academy in fulfilling its obligation as ambassador, advocate, and thought leader for RMIT. So before we start, so let's just get through some housekeeping things. This is a team live event, so you will not be able to directly ask any questions via microphone. What you should do is please post your questions in the Q&A sections during the lecture. So after the lecture, I will pick up those popular ones, ask the presenter on your behalf. Okay, so let's say a few words about Andy. The Distinguished Professor Andy Ball has been active in research in the field of applied environmental microbiology since completing his PhD at Liverpool University in 1986. In addition to publishing over 300 scholarly publications and graduating over 70 PhD students, Andy has also developed commercial solutions for the remediation of contaminated environments with 3 international patents. He has been awarded research grants and funding with a total value of 22 million. Andy has held various prestigious fellowships and given over 220 keynote presentations, both nationally and internationally. Okay, so without any further ado, please join me to welcome Andy to deliver his lecture. So over to you, Andy.
Thank you very much. Thank you for that very kind introduction. I'm very honoured to be giving this presentation today. It is a great privilege to be a member of Professorial here at RMIT. And today I'm going to talk to you about a project that really we're been undertaking here at RMIT for the last 5 or 6 years. And it's about a waste stream or an organic material that we really want to find continued use for as we go on in the future. And so it's about transforming Australia's biosolids industry and advancing that next generation of waste. And to give you a little preview of what I'll be talking about, I'm going to be talking about what biosolids are. It's a subject which not many people are aware of the term biosolids. In fact, interestingly, when we first were awarded the training centre, one of the branding people first questions were, do we really have to have biosolids in the title? So it's something that I think needs some explanation, and I'm going to get some help from my industry colleagues, and particularly Southeast Water, to explain that. And then I'll turn my attention to explaining what are biosolids used for in Australia. What do we do with this product? I'll focus particularly on probably the biggest use, and that's the reuse of biosolids in agriculture. And then I'll highlight the threats which are potentially might affect the sustainable future of the agricultural application of biosolids. A really significant stage, and really I reached the conclusion of the first part of the talk after point 4. And I hope at least some of the solution will be coming from point 5, and that's introduce to you and say a little bit about the Australian Research Council Training Centre for the transformation of Australia's biosolids resource, and say something about its uniqueness. So that's my aim for the presentation. And without further ado, I'll start with the first point. And that is, what are biosolids? And biosolids are defined as a stabilized sewage sludge.
Sorry,
yes?
We only see a fraction of this presentation.
Oh.
Yeah, so
okay, let me see if I can arrange that. Hold on, I may stop sharing for a second and see if I can improve the quality of that. Okay, I will try rejoining. Okay.
That's good.
Is that okay?
Yes.
Perfect. Oh, my apologies for that. I'm not sure what transpired, but to help me explain what biosolids are, I'm very pleased to have had the assistance of Southeast Water employee Andrew Gordon, and together with Aravind Soropanini, who's Deputy Director of the Centre, I've unable to take you there in person to a wastewater treatment plant, but I have some nice drone footage to try and explain to you what biosolids are and what stage they're produced. And this should at least give you some insight if you've never been to a wastewater treatment facility before. So here we are. This is from a drone. This is Mount Martha, a semi-rural wastewater treatment plant. And you can see the drone flying over the main introduction. Some labels appear. So this is where the main inlet comes, most of that water. On the right, we have the aeration tanks, and you can see the engine house, those microorganisms in the aeration, which would destroy the organic material. On the left, we have the primary sedimentation tanks, and those both generate waste and solids. Then we finally get the clear water in a secondary clarifier. And again, the solids from those three processes are the basis of the biosolids that are produced. This is Mount Martha, and as the drone flies around to the next area, I can tell you it was constructed in 1978. Here's the main office. This Mount Martha plant treats 13 million litres of sewage every day. And we're saying sewage is all the wastewater from toilets and drains inside a building. Quite amazing. And to think that 99.97% of this water is just water. 0.03 is the actual concentration of other compounds present in water. So as we go see, you can see it's a magnificent site, and it's a site of environmentally protected area. We start to see one of the things that we use for the last stage of biosolids. These are solar dryers, effectively greenhouse using the power of the sun to remove the moisture. 90% of biosolids is really moisture, so if you're going to transport it, you need to remove that quantity of water. So that's the last stage of the biosolids before perhaps its application. But first of all, following all those primary and secondary sedimentation, when you get the clear water, which goes on for reuse, all those solid materials in their water end up in these drying pans that you're beginning to see on the left-hand side here. And this is where literally the biosolids are left to dry out in the sun. You can see the biosolids forming on the right-hand side. So these are still sludge, which is beginning to be stabilized. And so these drying pans take up large areas, but it's a rural site, as you can see from some of the other footage. So it's quite a large area, so you can spread out that water. It's quite a shallow water, so you're trying to dry out as much of the water, leaving behind that sewage as you possibly can. And treating that much amount of water, 13 million litres a day, of course, you're going to need quite a large area. So there's a whole series of lagoons here, which are designed to act as to dry out those biosolids. So they initially get some of that moisture out, so we try and remove that water from these particular sites. And then finally we get to the area where biosolids are stored, and that you see at the top of the screen are the biosolids after drying. And there's some different ages. You can see plants growing out those on the left-hand side that have been stabilized. So they will stay there for some 18 months to 3 years to prepare them for biosolids for reuse. So you can see 0.03% of all that waste amounts for a lot of biosolids. So you can imagine how that efficient that plant is. But you know, to those of you who thought that the wastewater plants were very industrial, well, that gives you a different side and shows you how much the water companies really invest in trying to get an area that's as clean and pristine as possible. Next question, how much biosolids do we produce? Well, in Australia, we produce 303,000 dry tons, which is actually just over 3 million wet tons of biosolids. And that was in 2010. And that image of Australia on the right actually shows you all the wastewater treatment plants around the country. And you can see that they're focused around main cities, but nevertheless, you see them dispersed in Central Australia and other areas. So we produce them in all of the states. And on the left, that pie chart actually tells you where the main states for biosolid production are. And as you would expect, it will be New South Wales, Victoria, and Queensland, and then smaller amounts in Western Australia and the ACT in Tasmania and South Australia. But nevertheless, we produce 303 dry tons per year. It's a huge amount of biomass. And where does it go? What happens to it? It's a key question. So what do we use these biosolids for? Well, 55% of all of our biosolids that are produced are put on agricultural land. And I'll explain why that was in a second. 10% are used for composting. So if you go to Bunnings, sometimes some of the compost you'll buy there will have biosolids as a component of the composting process. So a little more is used in forestry. Unfortunately, some is still sent to landfill, which is something we really want to stop as we no longer really put that biosolids in the sea. That was prevented some years ago. We really want to divert all of this organic waste or material away from landfill. And as you saw, those stockpiles, 23% is stockpile, because once we drain it and we dry it, we need to remove some of the pathogens that may be there. And of course, there are very strict guidelines how we prepare that material for reuse. And that includes looking at levels of contaminants and also pathogens. So it's very well regulated industry that's ready for reuse. So that's what biosolids are used for. By far the most, if you include agriculture and composting together, almost 2/3 of all our biosolids will go onto the land. And that's a very important role that it plays. And it's a very sustainable role. So the reuse of these biosolids in Australia in agriculture, you see on the left the biosolids piles, the right it's being spread on the land. It's a significant opportunity and benefit. And in the time of closing loops and circular economies, it seems to make perfect sense that all the carbon and the nutrients bound up in these biosolids should be used to close that loop and be used for agriculture and that agriculture urban nutrient cycle. So it seems to be a very appropriate application. And why is it so useful? Well, if we look at the next slide, we'll see that this is the use of fertilizers in Australia over the last several years. And you'll see that green line is the amount, the top line is the amount of nitrogen. And nitrogen is a compound which is generally limiting in environments. It's the inhibitor that stops lots of organisms growing and changing that ecology. So in growth in soils, the addition of nitrogen will generally, along with phosphorus and potassium, increase the yield of plants, which in a crop system is, of course, what we've been trying to do. So you can see there's more and more demand, particularly for nitrogen in our environment. And of course, nitrogen is always very limited naturally on the planet. And especially the main form of nitrogen is nitrogen gas, which is not available for almost all organisms. There's just a few organisms which are able to assimilate nitrogen, fixed nitrogen. So the nitrates and ammonia haven't been around in nature for a long time. So we have to be very careful how we add that nitrogen so we don't cause any imbalances in our ecosystem. But nevertheless, there is a great demand in Australia for the nitrogen compounds and nutrients in general to improve crop yields. So there's a big demand for fertilizers and biosolids. So if we look at what is in a normal biosolids, that material you saw, you'll see that first of all, things like nitrogen are present, phosphorus, potassium, the things we just highlighted in that previous slide, along with lots of other trace elements which are required for growth of plants and other organisms. Sulfur, copper, selenium, zinc, calcium, magnesium are all present. And coupled to that, pH is generally neutral, so it's not going to cause a problem when you add it to the soil. And importantly, the organic carbon content is between 5 and 35%. So considering our Australian soils are very organic or poor in organic carbon, down to 1 or 2%, the addition of organic carbon is really a crucial step. And normal fertilizers, of course, don't do that. They don't have an organic carbon fraction, but biosolids do. So when you compare the major nutrients on the right, you'll see it's nitrogen, 2 to 6%, phosphorus up to 4%, potassium up to 0.75, and sulfur 3.5. Does that make it a perfect fertilizer? Well, no is the answer. If you look at the normal fertilizer that you can produce chemically, then the nitrogen content is much higher, up to 46%, phosphorus 22%, and potassium 50%, and sulfur 25%. So those compositions in traditional chemical fertilizers are perhaps very different than those you find in biosolids. But that's the same as most other animal-based manures. So I'm sure many of us would add dynamic lifter, which is chicken manure or cow manure, even horse manure to gardens. And they have very similar nutrient concentrations to biosolids. It probably doesn't surprise you because it comes through essentially in the same mammalian systems. So it's not a direct replacement for fertilizer, but it certainly has an important role to play in Australian agriculture. And that organic carbon is really important. That's what gives the soil a rich, dark feature, a bit like the biosolids itself. So for many, many reasons, biosolids is a very important addition, closing that loop, reducing our requirement for chemical fertilizers, which are also high energy processes, demanding processes. So we reduce our greenhouse gas footprint. So things look really good for why biosolids should be used. But there are threats. And so the reuse of biosolids has come under increasing threats in the last decade or so. And that's because along with those biosolids, with those nutrients, we find other products. We find metals, we find organic compounds, pathogens, of course, even nanomaterials that are present in biosolids, which may present potential hazards. And that will require assessment to predict and manage those risks and public perception about the quality of these materials. And of course, it comes as no surprise, whatever we use as a society, we will, of course, find its way into our biosolids. It'll pass through us, or anything we wash our clothes, or we use the bathroom, the toilet, will all be washed into the sewage, which will go to the material, and anything solid will end up in this fraction. So it's really an indictment of what society is using. And I think longer term, we may want to look at those, and we are starting to stop some of the use of the materials that are potential hazards. But nonetheless, in biosolids, there are a series of products, emerging pollutants that are present, which are environmental regulatory agencies are starting to question the potential sustainability of adding this material back to the soil. So we're looking at milligrams per kilogram of dry weight of biosolids. So it's relatively small concentrations, but nonetheless, they're broken down on this figure as persistent organic pollutants in the blue, bulk chemicals that we find to moisturizers and in our shampoos, and then a whole variety of personal care products which are related to triclosan in toothpaste through to musks and antibiotics all find their way there. And you can see that we find them all. Everything that we're looking for, we find. So polychlorinated aromatics, the first in the blue is probably the highest concentration, but you see quaternary ammonium compounds, QACs, polybrominated compounds, PDBs, which are present in furniture as a flame retardant. We have polychlorinated naphthalenes, PCNs, and polyfluorinated compounds, again in firefighting foam. It's something which is very topical at the moment. So we can see that we get a lot of compounds, persistent organic pollutants. Their very name tells you that they don't break down readily. They go through the wastewater treatment plant in large quantities, relatively large. So, and we certainly don't want them going through the food chain. High concentrations of personal care products, so anything we're using in the shower, the bath, is going to find their way through there. And of course, very low concentrations of some of these other compounds, but nevertheless, they have raised concern. So this is the threat. These emerging pollutants are causing a lot of controversy and questioning about the sustainability of this really vital product. So back to biosolids and the reuse program, there's increasing scrutiny of these contaminant additions to agricultural land. And this is not just unique to Australia. This is a global situation, global discussion. Public regulatory concern is rising regarding these persistent chemicals. PFAS, these polyfluorinated compounds, it's at the moment center stage in Australia because it's both persistent and mobile and potentially carcinogenic. So these firefighting foams with Teflon, all PFAS compounds, and are cause for concern, and they'll be found in our biosolids. So the likelihood is there's going to be revision of biosolid guidelines by a number of regulatory agencies. And new national environmental protection, ecological investigation concentrations, this whole new development could be applied to develop revised biosolid guidelines, which pick out some of these compounds of concern and will put limits on the application to agricultural land based around the concentration of some of these pollutants. So we really do need, nationally and internationally, we need to train, to research and develop biosolids reuse so we can move forward as a biosolids industry and find a potential reuse. So that's really the conclusion of my first part of my talk, and now I offer some way towards a solution. And that, of course, is the introduction of the ARC, Australian Research Council Training Centre for the transformation of Australia's biosolids resource. And this is based at RMIT Bundoora. We're in the first year, and it is a 5-year program. And it's the objective of this centre. It's about knowledge building, capability. So we're looking forward to the future of the biosolids industry and training the next generation of researchers who we hope will be the leaders, not just in research, but in the whole of the industry. And will be across these multidisciplinary issues and play a role in resolving them. So hopefully that will be the next management level of the industry and getting biosolids industry ready for the future. I'm sure legislation will be becoming increasingly stringent. We have to find new solutions. So that capacity and knowledge building is really fundamental to this training center. And of course, there's research development. So many of the industries have existing issues and have brought them forward through the process of application. So we need a fully implemented interdisciplinary program over the 5 years that develops cost-effective, obviously socially and environmentally viable, sustainable solutions for managing biosolids. It's not going to go away. They're predicted to increase with the population here in Australia. So it's about finding a reuse. And I should say that this is to the best of our knowledge, it's a unique centre. It is the only biosolids centre in the world. So although it's a global issue and we talk a lot with our international partners, we hope that this will be the world's focus for biosolids resource and developing solutions. And the third area is about sustainable strategic partnerships. So we have some fantastic engagement with industry, with government, with stakeholders about research development and technology. And we're going to resolve these emerging issues in the next 5 years. We're not going to answer all the questions, but we really hope to address some of the key ones and perhaps find a way for the centre to move beyond the 5 years. So it's a really exciting challenge, really exciting time, and I think we've got a great program of research. I'll just allude to a few of these things, a few of the areas, and a great team, which I'll introduce at the very end. So this is the transforming biosolids. We did manage to keep the term biosolids through our branding exercise, and you'll see our logo on the left-hand side there. And really, it's advancing both fundamental and translational biosolids research. We want to train new industry-ready researchers. We want to develop new applications and new market opportunities for the Australian biosolids industry. At the moment, biosolids are an expensive product for the water industry to produce. If they give it to agriculture, they tend to get very little money for it. And so it certainly costs the water industry, the water corporations, a lot of money. And of course, that means that all of us who pay our water bills and sewage rates also pay for these biosolids. So it's in the national interest to develop some solutions which perhaps leads to a value adding to this biosolids. And we have 3 main research themes. So one is improving the technologies. Can we make a better product? Secondly, can we enhance the product? Applications, can we find new uses for biosolids? And thirdly and finally, ensuring sustainability. And we don't just mean that it's safe to use, but also we need to think about social acceptance. I alluded to before the fact that we would all use a cow manure or a chicken manure in our garden without thinking about it. We'd have buy a bag of that at Bunnings. But if it was biosolids from humans, then of course that's a whole different perception and a very different thought process. And of course, although they contain almost the same nutrients, the origin, of course, they've been stabilized. It's still that question. So we really have to address that in the centre too. So it's not just about engineering or science, but we need social science as well. So we've incorporated all that into our 3 themes. And below is a whole series of links to the Biosolids Centre that were developed through the website or through LinkedIn and Instagram and Twitter. So we're trying to communicate to everybody to try and get people to understand what biosolids are, and perhaps once they understand the process, how they're developed, safety of the product, perhaps it will start to gain acceptance. So let's have a little look in detail about the improving the 3 areas of the centre. So these projects are just starting. We've been really fortunate enough to start hiring our postdocs and our PhD students. So the projects are literally starting as we speak. And in terms of improving those technologies, we're looking at existing but also alternative ways of preparing the biosolids. So improving existing treatment processes. Can we make a better product based on what we're doing so far, as well as finding whole new technologies to prepare the biosolids. Some of the issues with biosolids for agriculture are the fact that you saw that material, it's wet, 90% moisture as it starts. So you certainly don't want to be like Cleanaway or Veolia or Sewers, who are could be transporting mostly water, and that's expensive. So, can we make something with lower volumes and higher nutrient capacity? So we get a high value product like a fertilizer. We look at processes like anaerobic digesters and advanced treatment methods to help drying, hydrolyzing, producing off gases, and liquefaction, hydrothermal liquefaction. So whole new products, energy production, biochar formation from the biosolids. So completely transforming some of the approaches to biosolids reuse. This is, of course, something very close to a lot of water industry's hearts. It's very expensive. You saw the land that you need. So if you're storing biosolids, it's very expensive to keep finding land to store those biosolids. And that's what the water industry is facing with increasing legislation. So that's the rationale for why we have so much industry support. So really thinking about techno-commercial potential, but not just for not just for urban or city-based water treatment processes, but for the whole sector. That image of all those 280 wastewater treatment plants. We need to find solutions for as many of those as we can. So urban versus regional. But it's a tall order, but we have a great team of people, and what we think about what sort of a product should look like. So obviously we want it to be stable, it should be low in contaminant concentration, and it should be spreadable using existing technologies. But now we want to make it very low moisture. We want to improve the nutrient concentration so it becomes much more like a fertilizer. We need to control those contaminants. Odor is a very big issue, and of course it's the biggest complaint that wastewater treatment plants have received, or the regulatory agencies receive from wastewater treatment plants. So reducing the odor in the biosolids is an important process, and of course making it sustainable and safe as we go forward. So we have very good ideas, and we have farmers who are part of our centre too, as well as transporters, fertilizer companies, composters, all part of what we're preparing. So it's the whole of the industry, which is quite unique in the training centre. It really is focused on the biosolids chain. Improving technologies. Well, in total, we're invested, or $4 million are invested in this particular theme. We have 12 industry partners and 4 Australian and international university partners. And this image is one of the new approaches, and this is RMIT patented technology developed by Deputy Director Kalpit Shah, and that's some of the core equipment that will be placed in that image on the right-hand side. Those of you who know Bundoora, this is building 211. And this is where the pilot scale biosolids facility will be built, which is part of the Biosolids Centre. So that's will be ready in the next 2 months, and we'll be able to house pilot plant materials, pilot plant equipment developed here at RMIT, patented RMIT technology, and allow industry to assess its suitability as we go forward for biosolids reuse. So really exciting times for RMIT and Bundoora and the Biosolids Centre. So that will be opening within the next couple of months. We're very excited to get that, and had a great deal of support from RMIT to get to that stage, despite all the issues surrounding COVID. The second theme is about enhancing product applications. So can we transform biosolids into novel fertilizers, advanced materials for farmers? So almost customized fertilizers for specific crops. So we could make a specialized product out of the fertilizers using new technologies. And in doing so, we can develop more sustainable water treatment systems and farming systems by closing that carbon and nutrient cycle. Really, again, we really want the agricultural industry in Australia to continue using these biosolids. We understand there are some issues and we have to solve those issues to allow agriculture to continue. I think around about, there's very few countries in the world that use biosolids for agriculture in the amounts that we use in agriculture here. So we're a world leader in this particular aspect, and we hope through the centre to continue to do so. So this theme, we have $4.6 million. We have 11 industry partners and 3 university partners. I'll introduce you to them very soon as we reach the final few minutes of the presentation. As you saw before, that one of the big issues that the nitrogen and phosphorus content in the ratio is too low for most agricultural crops. So we have a lot of phosphorus in our wastewater, in our biosolids therefore, and we prefer, or crops prefer, more nitrogen than phosphorus. So we have to change that. So we have to manipulate the biosolids, and that, as we go forward, will create a higher nitrogen to phosphorus ratio, and that would be allow us several advantages. So we'll be able to reduce the biosolid application rates, because at the moment, to satisfy the amount of nitrogen required, we have to have a lot more biosolids and therefore a lot more phosphorus than we really should. So by equaling out that ratio, we will have the perfect amount, and that will mean environmentally sustainable, because we're not releasing excess nutrients into the soil, and therefore perhaps into the groundwater, into drinking waters, into receiving waters, and leading to processes like eutrophication. So it's great for the agricultural industry. And of course, we're adding the organic matter back into the soil, creating that rich, stable soil which can absorb and maintain higher moisture contents. We want to reduce those contaminant loading. I come back to that. That's a key component. Microplastics is something I haven't mentioned, but that's also something that is finding its way into biosolids. Anything we use as society will be in biosolids. Making it easier to spread. So at the moment, that powder, that soil black, is difficult to spread using conventional farming equipment. We need to improve that to make it easier for farmers to spread and to increase that grower acceptance. And one of the ways is perhaps by moving to a co-granulation or a compaction or pelletization process, where we're blending biosolids with other nutrients to get the right ratio. And in that little image at the bottom, we'll see Barham Water's pelletized product, which is much easier to spread. So we've already got some process and some progress on the way that we can move to enhance the product applications for agriculture. Finally, ensuring sustainability. No matter what we do, we have to be sustainable, and we have to convince people that it's a safe and good product to use, and that's crucial. So this is considering a number of topics central to the implementation of any improved management that we come up with. It involves environmental protection agencies, so we can talk about regulations. Can we have national guidelines? Involve the environmental agencies in every step of the way, and that should enhance our opportunities for getting any legislation, any agreement on the way forward. We need to improve community acceptance. It's every water company, every regulatory agency accepts this. We need to be better at communication to the community, and we're doing that as we can with the Biosolids Centre. We need to develop national guidelines, as I said, and a framework for evidence-based risk assessment, and it's of biosolids and any products that we meet, and measure public perception of these benefits of biosolid transformation. Really, we need to have social acceptability before this is going to be a product that can be value added to the water industry. Again, 5.7 million cash here, 12 industry partners and 5 Australian and international partners. As I said, this is a unique centre globally, so we've attracted a lot of attention and a lot of experts from around the world who have joined us. So as I move towards the end, I just want to highlight some of the acknowledgements and the key team. And the core management team are really set up by, as I said, Deputy Director for Academic, which is Kalpit Shah, based here at RMIT. We have a Deputy Director from Industry. We felt it's so important to engage industry. We have a lot of industry partners, as you'll see, that we seconded Aravind Sarapanini from Southeast Water for 2 days a week for the life of the centre. And he's been instrumental in really making sure that we're addressing industry requirements. And I'm really fortunate enough to have a centre manager. Again, RMIT were very helpful in creating this position. And Elisa McElroy has taken that centre manager. And those three are really at the engine house, supported by our 3 theme leaders. So Damien Badston from University of Queensland, who's in charge of Theme 1. Megan Ryan from University of Western Australia, who's looking at Theme 2. And Richard Stutz from University of New South Wales, who's in charge of Theme 3. And we have a lot of CIs, and I'll mention the 2 from RMIT, Dr. Sarvesh Soni and Professor Lauren Rickards, who are both playing different roles, but crucial roles in making sure that our projects are running on time and alongside the requirements of industry. Of course, Lauren's very much involved in that social side, social acceptance, and looking at energetics and greenhouse gas emissions from those products. So our 10 projects are distinct projects, but they're all interlinked through those 3 research themes. We have a fantastic strategic advisory committee who really sit above us and tell us what's going on and where we should be. Training committees, communication, all these things are crucial. And we're just organising our first annual symposium at this moment, and together with a launch. So we're hoping a launch in July, when we really like the Minister for Education to come from Bundoora and open up at the same time as our first symposium. So very important period of time coming up. And finally, acknowledgements. You can see all of the universities, Arizona Imperial College, are our international partners. The water industry has been sensational across Australia. And those in blue there, the light blue, are members who have just come in to join us since we've started. So we're a growing band. And Andrew Gordon, I thank him for that drone image to help me explain what biosolids are. And lastly, thank you all very much for your attention. Thank you.
Thank you very much, Andy, for a fascinating talk. We got a few questions here, so you might just provide some response. The first question, so what do you think is the source of pathogens found in the biosolids?
Okay, so that's obviously the main source is from fecal material. So, you know, from households, a lot of fecal material, and 1/3 of the weight of fecal material are bacteria. And of course, many of them are very important commensals to us. We require these organisms. But of course, we do have pathogens that travel through us, be that viruses, be them bacteria, be them eukaryotic organisms, worms, for example. And so by far and away, it's coming from human intestinal systems. But of course, might also come from dogs, cat feces, and other animal feces. So far and away, it is fecal material that is the key provider of the high number of pathogens that we find.
Okay, thanks, Andy. Here's another one. This is a long one, so be in mind with me. Residual is obviously always expensive to treat after any wastewater purification processes, including brine treatment. In the past, there has been some resistance from water authorities, including Melbourne Water, Barron Water, to invest in anaerobic systems for biosolids treatment and stabilization. Not now. What is your view regarding most effective treatment system which have short treatment time and small footprints, and indeed low energy consumption for treatment?
Thank you. I think I've got that question. Thank you, Zing. So anaerobic digestion is something that's it's a key area of one of our projects that I'm involved in, and looking at the problems associated with anaerobic digestion. But in terms of reducing the volume of biosolids to obtain a renewable energy, be it biomethane or even, as we're looking at now, biohydrogen and volatile fatty acids, it is an extremely effective way of capturing energy from biosolids and transforming that product into a recalcitrant material, benign, killing pathogens. So I'm very much in favor of anaerobic digestion systems. I think they're going to evolve in the next 20 or 30 years. I think the water industry will look at the products besides just biomethane from those products. But of course, in the image I showed you from Mount Martha, this is a rural site, and so with a solids component of 0.03%, it's not enough to get a functional anaerobic digester there. So they're very much small footprint, but usually used most beneficial where you've got a high throughput. Rural systems depend on those lagoon systems, which I agree are not ideal. And perhaps there is a way of moving those systems on. Anaerobic digestion would be a very effective way going forward. And I hope some of our research will develop new value-added products from anaerobic digestion. Precursors for plastics is one area. We can produce volatile fatty acids, which are fantastic precursors, by manipulating the microbial system. So I'm hoping we'll offer solutions for not just urban, but rural use of anaerobic digestion as we go forward.
Okay, thanks. And here's another one. To what extent do you think converting biosolids to biochar can solve the contaminant problems faced?
So I think the research done by an RMIT person, Kalpit Shah, has shown that actually through the biochar process that he's developed and RMIT patented, the levels of contaminants are significantly lowered and if not eliminated by the biochar process that he developed. And those that are still there appear to be non-biologically available, so they're locked up in the char, and therefore it appears that they might be a very useful product to reduce and even remove some of those pathogens. Of course, this is early stages. We need to do more field trials, more research to look at that. But I think biochar is one solution. I don't think it is the solution. There are many others that we need to develop. So that's why we're not reliant on one technology, but we're trying to look at the different requirements of the water industry. And biochar production is certainly one aspect that is gaining significant traction with the water industry at the moment.
Okay, thanks, Andy. I just have a couple of questions myself. From I'm sort of electrical engineer, so this is absolutely new field to me. I'm just wondering. We know the environment impact, how to processing the those kind of biosolids. But what are the business model? Are they sort of usually the government-owned entities or the privately owned entities? I mean, how those kind of a cost benefit usually? Because there's an issue, of course, with those kind of different model, the impact on the quality of products.
Yes. So these water companies are state-owned. They're water corporations. So, they have a duty to carry out all of these tasks and are funded from the state government. So which consequently means that such as biosolid centers like this, these water industries are not competing against each other, which is really important. There's a great collegiality about the interactions of the water industry, and I think that's really borne out in this sense. And the fact that, for example, 6 new companies from Tasmania, from the ACT, Icon Water, and from Sydney, New South Wales are joining us. That only leaves us, with Northern Territory to really try and get somebody on board, and then we've covered every state. And that, to me, tells you a lot about the water industry and how collegial it is.
Mm, yeah, but how do we benchmark against the international, other countries? Are we? I mean, we all know that our water is pretty safe. You can drink from the tap water. But if you benchmark Australians, how do you rate it? I mean, who is the best?
So I think Australia would be right up there. I think in the last 10 or 20 years, then I think European Union have funded a lot of research into developing new technologies, because of course by 2050, Europe and all these the water corporations must be carbon neutral. So they've really looked at the future, and that's why we're trying to bring some of that knowledge to this centre, because I think in the future they have probably done a lot more research, but at this moment in time, US, Europe, and perhaps have got more research. But in terms of the legislation, Australia is right up there in terms of the highest quality of the water. And I think with this centre, we really hope to make it a focus for the biosolids research as a global phenomenon. Okay,
thank you very much. Just a very trivial question. Why water tastes different in Melbourne and Brisbane? They all have slightly different taste. Is that because of the, the thing, geographically?
Yes, you're quite right. And so when I first arrived in Australia, I found myself in Adelaide, and that water was actually coloured, quite yellow because of the humic substances. So it's very much a reflection of perhaps the groundwater that it's come from, or the rocks that the reservoirs are stored, the basis for the reservoir. So yes, there is a very much flavour from the local topography, the structure of the rocks. So you will see some variations. They're actually tiny when you look at the analysis. I mean, they're almost identical, but very small tastes. Our palate is very partial to picking up and detecting differences.
Okay, thank you very much. I can see, I don't think there's any more questions, and we're already sort of close to the end of the lecture. So on behalf of everybody, so thank you very much, Andy, for a fascinating talk. And thank you everyone for attending, and we hope to see you in the next lecture. Thank you very much.
Thank you very much. Thank you, everybody. Have a great day.